Hi, how are you guys doing today?
So I'm gonna do live. Do you have like the videos up?
I do not yet. I'm working on them right now, and I
Okay.
had a few little technical issues, so I had to restart some things. So no, I don't have videos. I'm going to post one with the direct delta function like properties and the derivations of all those, so they make a lot more sense. I know that was a little confusing from class on Monday, and then I will have the last example of the one where you use that sinusoid as an input and no longer have u at t. So I haven't posted those yet. All right, general questions you guys want me to go over?
This is Ian. I've got a general question.
Uh-huh.
In the previous units, I've always felt confident in knowing what it is that I'm trying to do, and you do a really great job of providing like here are the steps to solve each problem. But with this unit, it seems like we've covered a lot of things such as AC sources, filters, power, and now Fourier. And I'm wondering if you could maybe summarize what Unit 3, like what are the principles that we should know for Unit 3 and maybe methodology for solving them.
Okay. Yeah. So let me share my screen. I can find, how do I have my iPad plugged in a little differently. Okay. So I'm working on the videos right now. So this is why you see this video screen. So let me see if I can get rid of the other. Okay. So just ignore that you have two of me on here right now.
No problem. OBS is cool. That's cool.
Yeah. So I'm trying to, anyway, I was having some technical difficulties, but I think I figured it out. So these will be the other videos. So on this, okay, so for the first one, it's like really understanding the terminology for the power and how to calculate those values. So what does average value mean? What does RMS value mean? What does complex power mean? What does apparent power, average power, reactive power, and the power factor, and understanding the leading or determining leading and lagging. So it's mostly just understanding the terminology and then how to get those actual values. Do you want me to go here? I'll summarize this and then we can go back and go over like this would be how to calculate them. Okay.
Awesome.
And then the other one is the load impedance, so that the power dissipated is at a maximum and how much power that will be.
Okay.
So that will be the second type of thing you have to understand. And then the third one is identifying filter types created from a circuit and then determining the bandwidth of that and the quality factor and the resonant frequency if applicable. And then those corner and cutoff frequencies.
Okay. Is that the whole like V out over V in? Is that with filters? Like H is equal to V out over V in, something like that?
So that's going to be the transfer function for any type of
Okay.
circuit. So that concept of, I'll add that to her transfer function concept. That's a good one too. So yeah, so the transfer function concept of that V out over Vn. And, we've done it all the time. That's basically what we're doing, but we usually have specified what our Vn is. And the difference with now, like looking at like filter designs and some other circuitry is that Vn is not defined. You're using it as a variable. And so that's kind of the difference that we've moved to and why we call it a transfer function when Vn is a generic Vn instead of one specific input. Does that make sense?
Will we have a value for Vn eventually? Like, do we either solve for it or will it eventually be provided, or is it just stay as a variable?
So for filters and amplifiers, you always leave it like in a generic form. And the reason is that you want to get this graph and the Bode plot graph.
Oh, okay. Yep. Therefore, you need a variable for it because okay, that makes sense.
Yep. So we don't want to define it at just one location on this graph. We want to know it over a whole variety of frequencies. What does that look like as we change frequencies?
Okay.
So that's again going back to like, what are we trying to get out of this? And in that case, we're trying to get out some different information. So this was also an introduction to Bode. What is a Bode plot?
Gotcha.
So these are kind of, we've gotten more into like concepts now, because all of these concepts are kind of new. And then some of it is like, oh, okay, well, if you understand what that means, you can look at this value and say, this is what that value means. And
Okay.
so, and look at this and say, oh, this is a low pass filter. So it's not necessarily a lot of calculations this time for those things, but it's more understanding what the terminology means.
Okay. Yeah, it just seemed like we moved a little bit away from solving the circuit and more focused on like, here's an aspect of the circuit. What does it mean? Okay.
And this is why, because we're just doing like the basic foundations of understanding these, and then you're going to use all these concepts in follow-on classes.
Okay, great.
So you'll get into a lot more details in follow-on classes, especially power. There's a whole power class, but understanding like the beginning concepts is what we just need those terminology for now.
Okay, that's great.
And so that's why these three are going to definitely be more like, what do these mean? If I look at an equation, how do I identify those values? There's a couple calculations. I mean, there's calculations in the power itself,
Yes.
but they're more like understand these formulas and being able to put the numbers in them.
Right, similar to the quiz that we just took on power. Okay.
So that's really all you're needing to know from those. Number two, you do definitely have to do calculations too. So I'm going to go over a lot more examples of those. I only did one for now, and then I wanted to kind of cover the rest of the material, and then I'll go over some more examples. And if I have time, I'll actually post some examples for this Wednesday. But if not, I'll just have them available for next week.
Okay. Great. Yeah, I think finding R Thevenin would be really helpful.
Yeah.
For sure.
Yeah, I think that's a little weaker for most students. And so definitely need lots of more practice on that one. And then this fourth one will also be a calculation where it's more circuit analysis. So the fourth one is being able to do the Fourier transform using a non-periodic waveform. And so that's like the main one, is just applying the Fourier transform technique, right, which is underlined. And so you do have to kind of understand now with this, there's the delta function properties in order to be able to solve some of these.
Okay. And okay, so a thought just came to my mind. I've been asking myself, have we been dealing with AC for a while? And I just realized we've been dealing with AC back with Laplace, right? Just periodic alternate. Oh, okay.
Yeah. So this whole time we have been looking at AC this whole semester. We've just looked at different ways of solving now AC, and then the limitations of each one. And each one yields a little bit different information.
That makes sense. Okay. Plus, yeah, with our answers given in a U of T with, it just clicked that we've been doing AC for a little while.
Yeah. Okay. So the Laplace has been all AC. It's only just everything's U of T. So it's after time that you define as 0.
Okay. Wow. That was big for me. Thank you.
Okay. Yeah. So going back to kind of summarizing, like this one, let's see, 15. So like here is going to be like understanding how to calculate each of these. And then, complex power, that average power, reactive power, average and real mean the same thing. And then the power factor and the relationship of that. So these are kind of the summary of like, here's your equation set, understand how to find these values.
Great.
And then summary of maximum power transfer. So I don't have these like written out well, because it's just really two steps. First is the VTH, and then, 3 steps. Maybe I'll write it. Find a spot to write it. Okay. So find VTH by placing an open
over the load.
Yep. Between A and B of where load was. And then 2 is to find ZTH
Which is
by,
like the opposite or the conjugate of something, right? Or when it equals the opposite, something happens.
so Z load that you want to have maximum power transfer.
Okay. Oh, right, because they go up to zero, zero meaning the maximum. Okay.
Actually, there'll be 4 steps. So Z load will actually be the complex conjugate of ZTH. And to find
right.
ZTH, you're going to remove independent sources.
By setting them equal to 0.
Uh-huh. And then pathway between A and B.
Okay.
And then once you find that, then you can do the Z load, which is going to be the complex conjugate of ZTH. And
Right.
then you can find the max power. By 1/8 VTH, the absolute value of VTH squared. So the magnitude of VTH squared over 2 or 8, sorry, 8 or real part of VTH.
Okay.
Trying to think how to, I think the real of ZTH. There's a better formula for you. So those are the kind of the steps, those are the 4 steps for the maximum power transfer.
Great.
And then let's see, what was the other ones? Okay, so then for the Fourier analysis is going to be very similar. Fourier transform analysis. So this is going to be very similar to the Laplace. So with that one, you're going to change to J omega domain. Or you can do it if you like, just S.
S. Yeah.
And then at the end, before you translate back, just substitute S equals J omega.
And you prefer keeping it in the S domain instead of or keeping it as an S. Okay.
I do. I think it's easier to manipulate the equation, but again, okay, so then you're going to change to the JW domain, and that means all the elements and the input source. And then you can, some of mine I don't translate the input source till the very end. And again, that makes that math a little bit easier sometimes.
Yeah, that was great that we did that in the lecture class. I thought that was helpful.
Yeah, I think that little step in there usually makes it a little easier to manipulate the equations. And so then from here, you use circuit techniques. Usually I use
node voltage.
Node voltage. To then get the to get whatever variable you want to obtain variable. And then from there, you're going to then do an inverse Fourier. Back to time domain.
Okay.
And so with this one, again, you may need, you have to understand one other concept is the delta function properties.
Yes, because that was the hiccup with the 10 something cosine.
Yep. And one of my videos will be on that. And then the other one is that you also may need to use the partial fraction expansion again.
Cool.
And so those are kind of the other kind of things that you kind of need to know to kind of solve for those.
Right. Yeah, that makes sense. That's a really good holistic picture. I'm not missing as many concepts as I thought I was.
You know more than you think you know.
Yes, yes, that is true. Yeah, thank you.
You actually know a lot. And so, yeah, hopefully this gives you more confidence.
Yeah, 100%. This is a great, like I said, great breakdown. Thank you.
Okay. Yeah, no problem. Other questions from anybody else? Do you guys want me to go over the delta function?
Yeah, I think delta function would, if no one else has anything immediate, I think delta function would be a great one, just because that table might not have been completely developed, and also just some practices finding z Thevenin. I think those would be great.
All right. So going back to the delta function. So the delta function is usually, this is the way we graphically will see it. So you'll have it at 0 and there'll be delta, delta t or delta omega. That means it's at 0. If there's a number in front of it, even though that's not like a realistic. So this is actually like you can create the delta function as this formula. So it is exponential
Wow.
squared. And then as you change that exponential, you can actually get more and more of a spike looking thing. And so, if you were to kind of, all this is like modeling like a spike in the system.
Gotcha.
And so sometimes we want to put a magnitude to that spike. So sometimes we can say, oh, it spikes up to like, oh, I can see it looks like about 100, so we would say it's 100 delta t.
Delta t, yeah, okay.
Yeah. And so that 100 we want to still use as like a magnitude to help understand more of what's going on in the system. So sometimes you'll see that as like 10 delta t. That 10 just means like, yes, while it's like still a spike and goes to infinity, we sometimes will put a magnitude on it. Then the delta t shifted is t minus a capital T. So that's when you're going to see that delta t minus
shift.
T shift. And so that means that it actually is only at that T value, that capital T value. And so those are the 2 times that you're going to really see it. And so this is kind of how we loosely define the delta function. So it will be like an infinity at x equals 0 and then 0 everywhere outside of that. And so that's kind of a property that you need to understand.
Does that infinity, like, will that be limited by the magnitude? So like if it's 10 delta t, then at 0 it would go to 10.
Yeah.
Okay.
Yeah. So we just kind of say what this means is that yes, it's valid at t equals 0.
Okay. That's okay. That makes sense.
And if it's shifted, it will be valid only at that one value.
Gotcha.
And if you have a magnitude in front of it, we call it that magnitude value.
Gotcha. So it's like on or off, in other words.
Yeah. Okay. So like on or off. And then the other thing that we constrain it to is that the integration of it, because it's only valid at one value, we define that as being constrained to be an integration of 1 at that value.
Right.
So it's like just a very small section underneath the curve and we give it 1. So if it was like 10 delta t and we integrate that, we're going to say it has a value of 10.
Right, because the 10's a multiplier. So yeah, exactly. And it can multiply another one.
It will multiply that. Yep. Okay, so that's the property we're going to use then to derive everything else. So now we have this time where you always have maybe a function multiplied by the delta function, and then you're going to integrate it. So in Fourier transform, that is always going to be the case. Some function and delta dx. And so what we find with this is that this is always, when it's integrated, is going to be f of 0, because the delta function is only defined right at 0. And then integrating it will be like, if you multiply it, it's only going to be valued or value of that delta
at 0
right at 0. So that means f of 0, right? Because f of 0 is going to only be 1 point right there. So you would have 1 point of that multiplied by, like, yes, it's valid at that point. And then you integrate it, and the integration yields 1 for the delta part of it. And then the function itself only has the 1 value at f0. So when we integrate that, we only have to define it as f0.
And so question then, what if there's a shift?
And so yes, so if there's a shift, then it's just going to be valid at f of a.
Cool. That makes sense. I assumed as much. So in that, I'm just using memory here, so it's probably not perfect, but in that 10 something cosine, would that f of x then be that cosine, for example, and then this will be cosine evaluated at 0?
So in this one, we had, so this was the example
That's right.
that we had done in class. And I said, well, this goes to 0. And so I can define this a little bit better. So the reason it goes to 0 is because when we integrate, we're only going to take the function at 0, and then it's integration to 1. And so, when we plug this in, this is 0, this is 0, this is 0, and this is 0. Or sorry, this is not 0.
Oh yeah, so it's with respect to omega, therefore the 0 is getting substitute, or is getting in, the omegas are zeros.
Omega will go to 0. So
okay.
This becomes, e raised to the 0 becomes 1.
Okay.
So, this goes, wrong one. This goes to 1.
Okay.
But this is a j times 0. So that whole top is basically going to go to 0.
Right.
And so because of that, the function then all goes to 0. So the integration then goes to 0 because of this portion.
Yep, that makes sense. What happens with the delta omega next to the 10 pi?
So remember, the integration of that becomes, so all these other things become a value. So they get brought out. So we have 0 times the integration.
So that's the f of x part, right?
Yep. So this is the f of 0 part.
Right. Okay. Okay.
And then this portion becomes 1.
Okay. Oh, okay. Okay. Okay.
And then it's 1 times 0. So it goes to 0 too.
Right. Right. Okay.
So with the cosine portion. So you translate the cosine into the Fourier, which ends up being this kind of yucky shifted omegas. And then it ends up, being this.
Yes.
And now when we integrate this first one, again, it will, because of that j omega in the top,
that will go to 0.
That will go to 0. And then the second one goes to omega equals 4.
And it's the omega in front of the delta that goes to 4, right? Not the omega on the inside?
Correct. So the delta omega minus 4 will integrate to 1.
Okay.
But the omega in the front of that goes to 4, and then the omega on the bottom goes to 4.
Okay.
And then this one will go to a minus 4.
Oh, so it changes because those two functions are shifted, therefore the omega is different.
Yep.
Whereas the one that's not shifted goes to 0. Okay. Okay. Yep.
And so that's how that one will work.
Okay. I think the part that I'm still hung up on is if we look at the shifted functions, there's an omega on the outside and an omega on the inside of the parentheses. The omega on the inside of the parentheses, I don't touch, right? And I just evaluate the integral of that.
Yeah, so the integral looks like this one.
Okay.
And then you bring out the numbers, and then this portion here.
Yes.
Will go to integrate to 1.
Oh my gosh. Okay, so no matter where it's shifted or whatever, that will always go to, that's nice. That's so nice.
That one always goes to 1. And so you just replace omega with the other numbers, and then the integration.
So it's literally either always 0 or 1. It'll either evaluate to 0 or it'll evaluate to 1. I think I'm getting it.
It depends. Like if this was not shifted, then that omega, this omega, will go to 0, and then that whole term goes to 0.
Right, but that omega, there will be a 4, and then that delta omega will go to a 1. Okay. Okay.
Yep. So this becomes a 4, which means this whole portion is some number.
Yep.
Along with this will then become a number,
which can get pulled out.
Yeah, and all those become pulled out, and then you still have the integration of just delta omega minus 4,
which will be 1,
which will go to 1.
Wow, that's so cool. Okay, thank you. Wow.
All right. You had said you wanted, let's see. Let me think if I
Before we
can.
continue,
Yeah.
can we go back to like the integral with delta x minus a to like equals f of a? Sorry. Could you elaborate on that?
This one here?
Yeah.
Okay. So do you understand why this one goes to F0?
Not quite, sorry.
No worries. Okay. So I think this spot here. Let me open up another window. I'm like, there we go. Now I can write on it. Okay, so you have a delta function. And say I have an f of, let me do these in different colors, an f of x. Okay, so I have a delta function and I have, some cosine omega t function. So if I multiply these two together, and integrate them, and say this is 4 cosine. The 4 comes out, right, as far as the integration. Right, Lawrence?
Yeah.
Okay, just want to make sure you're still following me. Okay, so everywhere outside of the delta function is 0, right? So I have 0, 0, 0, 0, 0, 0. So all of these are multiplied by 0. And so this only can be integrated right at this one specific point of 0, right? Because I'm going to have so this is the property of delta function. It's not really a value. It's just saying like, oh, you have a valid value at that point. So I'm going to only have 1 point from f of 0. So this is going to be cosine of 0, which then is some number. And I bring that one out. And then I have this is my definition that this equals 1.
Weird.
And so this is just f of 0 times, 1.
Okay.
So what this basically means is f of x times the delta function of x will always equal that f0. And that's because you're only getting one value here. And
Is
then
there a difference between having like f of x and then the delta function of d of x, or is it delta function of x times d of x?
delta
the way
function, say that again, the delta
you
function.
have like f of x times the delta function, and within the delta function's d of x. I'm assuming it's not much different.
Oh, yeah, they're the same.
Yeah.
So you're saying this portion.
Yeah.
Yeah, they're the same. Just different ways of writing it. And again, that's
Okay.
a property of just the delta function is not really a real function. It's a model of what's going on.
Okay.
So the delta function is not considered a nice function. It's got its own little weird things to it.
Mhm.
Does that help?
Yeah. And
Okay. So once you
Just-
understand that, hopefully you can understand that now, like if I shift it and that delta function actually is only valid at a, then the integration is going to be f of a.
Okay. Yeah. All right. Thanks.
Yeah. All right. Other questions? Okay, let me find. I'm trying to think of, I don't think I have a lot. Find a problem.
Thank you for your time, by the way.
Yeah, no problem. Yeah, let me get a max transfer circuit that we could work on.
Oh,
Love all the authentication stuff. Okay.
so while you're pulling this up, just a general question for calculating. I'm not the most proficient with MATLAB, but it just seems like from the work that we've done, I don't have to create any crazy functions. It seems like I can just do computations such as matrices being multiplied together in MATLAB to help, right? Like I don't need to generate any crazy functions for this necessarily. Like it all can just be done through basic computation.
So the delta function, that's why you have to understand the properties of it. The delta function is hard to put into like MATLAB.
Okay, but the right, but what we just went through that seemed really simple.
Mhm.
It's yeah, that it'll take either f of 0 or f of a. So, but outside of that, everything else is like pretty much systems of linear equations and basic computations, right?
Yeah.
Okay.
Maximum PowerTransfer. Okay.
Yeah, I guess the delta function would take some work on MATLAB. I can see that.
Is this the one I did, or is this different?
It's a good question. I'm not sure.
I hope it is different. Okay.
Okay.
New one. Yeah, I just want to make sure I'm not doing the same ones. Okay.
Well, we have an updated table that has the properties of the delta function.
Yeah, I can create that. Okay, so here is a circuit. If you guys want to work on this, so you're going to need to find the VTH and ZTH for that load. And you're going to have to do it generically with like V1, R1, Z, C, and ZL.
How do you evaluate the V1 with the angle? I think I missed that day, and I'm not sure what to do when there's an angle, like a shift there.
So what that means is it's just a phasor of the V, so it's already been changed into that S domain. So you don't have to
Do anything necessarily?
know what that form it looks like is V1 E to the J.
Oh, we just gotcha. So we just take whatever angle that is. Okay, and then we say it's in polar form. Okay.
So this is already given to you. So this is the same. It's a different way of writing the polar form when you have
Right.
that angle form.
Okay. And that e to the j omega, is there a table like identity or yeah? I guess you wouldn't need it. Well, okay. I guess what I'm trying to say is because I don't inherently see an S value, I'm not quite sure what to do.
Yeah. The table go. So just write this. I think of an easy way to describe this. Okay. Where did it go? Oh, I put it down here. Okay. So before you just oh, I didn't finish solving, I guess, this whole thing. So like I usually generically solve it like in terms of the V, and then at the very end, I'll put the V in. So in
Right.
this case, like the V is going to be, where'd it go, V1. Oh, X minus.
So if we had, I'm just thinking generically speaking, if we had V1 was equal to 5e to the j 30 degrees,
Mm-hmm.
that would just evaluate to a number, correct? And we would just use that, what you just wrote down in our calculations, and it would work out.
So,
Oh,
so this is the time domain expression of that.
right.
And then the EJ to the 30 is a phasor form of that. So if you're solving for, like if you're using Laplace still, then that makes it easy because you're assuming that everything after it, like everything still has U of T to it.
Right.
And so to find maximum power, that's usually what we do is we'll assume that. So we're not moving to Fourier here. You just assume that it is like has a U of T to it.
Okay. So we'd assume that the V1 would be 5e j to the 30 degrees U of T.
30 degrees U of T, yeah.
Okay. So my next step in my head would then be to look at the table and see how to substitute it to do the Laplace to get an S value attached. Like that would be my next step. Would I be mistaken in that?
So if I was to use like the Laplace here, to the Laplace. It was 2. So that's going to like translate as 1 over S plus A.
Okay. Okay. Yeah.
And A at minus A in this case.
Right. Is A theta or is A the degrees? It's the coefficient in front, right?
So this is where it's kind of confusing because the phasor is written there, but like if I was to do the cosine, it's actually going to be this one.
The S plus A over it's that one, yes. Right. I guess maybe to simplify my question is with that V1 having a value and then a phasor shift to it, I'm just not sure what to do with it. So that's all. I just don't know what to do with that.
Yeah. So there's a little bit easier thing depending on what you're looking for. So here all we need is the magnitude of V.
Oh, okay. That's
VTH.
nice. So we don't even need the right. Okay.
You don't need the angle portion.
Oh,
So
okay.
you can just use the 5.
Gotcha. If I make things needlessly complicated, feel free to stop me.
No, it's okay because I'm trying to be like, yes, those are the whole steps, but there's like a little bit of all you really need is that 5.
Okay. So okay. So chances are in a circuit analysis question, not for maximum power, we wouldn't see like a voltage and then an angle to it, and then like right.
The angle's not going to change it.
Oh, okay. The angle.
It's
Okay,
not
the
going to
angle.
change the magnitude of it.
Okay. Okay. That makes sense.
And then it's not going to have any effect on the ZTH portion because you're only looking at the elements themselves.
Okay. Okay. Okay.
So in this case, what happened to this one? So you can just use the magnitude to solve for the rest of this. So you can just do, VTH and then the magnitude of the V1
Right.
to get VTH. If you want to go ahead and do that and then also try and get ZTH. Lawrence and Miles, do you guys want to try this too? Or do you want to work on something else while Kane does this?
I'm happy to follow along here.
Okay. So you guys take a minute and work on this and then I'll go through a solution.
Can you quickly scroll up to the
Yep.
answer and the question? Thank you.
I think I found ZTH maybe symbolically. Oh, never mind. Voltage source when it goes to 0 is a short, not an open. Flip.
So can I ask for like clarification with the thing up top? Like, is it Z of C equals Z of C times J?
This
Or
is
is it
ZC, it's the same, not writing. It's just some number, like this will be minus 5J. Like this would be, maybe 5J. So
okay?
CL just, it has the J, or you
You
It's
can,
like
mean
a
like the
placeholder.
magnitude of
it's just kind of
okay.
replaceable, yeah.
Okay.
So the J is in with the ZL.
Yeah, I think we could just use the bolded portion.
Yeah, you can treat ZC as like a minus 5J.
All right, that makes more. I'll just treat them as themselves.
Good strategy.
I forget how to solve this Mario. Oh wait, god damn it. Okay.
Here's a hint. What's here? Current.
Where? Oh, 0.
There you go.
Well, I'll mute myself.
Oh
Thank-
yeah, flip. I
You.
forgot to do the second part.
Oh, I think he kicked himself off.
That was him who left. I didn't see. Dang.
Yeah, I think Lawrence just kicked himself off of that.
Yeah, circuits is tough. Okay, so I gotta find VTH. So we know VTH is equal to Vx minus 0 over ZC. Welcome back.
Welcome back, Lawrence.
I is equal to voltage divided by resistance. Okay, so voltage is equal to IR. So VTH is equal to the current. Oh, is VTH just equal to Vx? It is equal to Vx. Okay, Vx is equal to. Dang it, that's too bad. Did you end up generating values for each of the components?
Just for this example down
Okay,
here.
great. Thank you. And this is the same circuit, right?
Yeah. Yeah, I was just doing an example of the math for
Okay,
this.
that makes sense.
Does finding VTH help you just find Pmax, right? Or is it P average?
Yeah, the P max, correct. So you're just looking for the magnitude of VTH. So you don't even have to solve for the angle
Oh, okay.
typically. I did something wrong in my math because Wolfram says that this is equal to 1.38. Plus 1.45J.
I have 1.38 minus 5.45J. But I could be wrong.
Well, I used Wolfram. I did minus 2J plus 1 over 10
Plus 1 over 4J.
Okay. This is what it ended up saying it was.
Well, what the heck?
8 plus 1.45J.
I used the TA84 calculator if you want to try that out.
So 40J on the bottom.
Yeah, I tried it again.
It is also saying that this would be then 1.38 plus 3.45J.
That's so weird. I got minus 3.45. I'm trying it. I did on my calculator, but I'm trying on a Wolfram right now. Yeah, Wolfram's giving me what I got, which was 1 minus. So it's the 1.38 minus 3.45, and then minus 2i.
And you're using 4J, not minus 4J.
Pardon?
Do you want to share your screen?
Yeah, yeah, it honestly could be a typo. Yeah, that'd be. Let me do that. Okay. Is it coming through?
Yeah.
Okay.
1/10. That is weird. 1/it's just doing 1/4 and then multiplying I.
Oh, what the heck? Okay, so I have to group the 4i together
Yeah.
too?
Or do 4 times I. Yeah, plus
Wow.
5. 1.38, yeah. So that's
What
the
the
same
heck?
as I thought.
My fault. My fault. Thank you. Thank you so much.
No worries. Sometimes it's easier to see when you're like looking at it from the outside.
Yeah, I cannot believe. Okay, I have to group. Thank you so much. Like you taught me how to avoid this mistake in the future, so this was still invaluable.
But the strange thing is anyway, something was wrong in my math. And somebody had asked me to like start writing out the whole math. And this is one of the reasons I'm like, it's better to use a calculator because then you don't make errors. So I have an error in here somewhere.
Do you? Because we have the same answer though now.
No, this 1.38 plus 1.45J
Okay.
Wolfram in the black.
Oh, okay.
And my
Well,
answer is
okay.
blue. So
Well, I think so. I've also asked for the math to be shown, but I think if you can show that you're using like just that. Sorry. Let me put it this way. I think if you show like, hey, I'm using Wolfram here, that is also acceptable. I just think a lot of times we're like, how did you go from A to B? And if it is, and sometimes we don't know that you're using a calculator. Like part of me sometimes thinks, man, professors have like this bag of tricks, of algebra tricks that they know how to do. And I think we're also really taught not to use calculators, and then suddenly the math gets tough enough and it's like calculators are okay.
yeah. All right, I'll just do it from here and
Cool.
just use that for Wolfram.
Okay. See that? Yeah, that explains it. Yeah, that's awesome.
And then that gives me that answer.
Okay.
So now from here, what will ZL be?
ZL will be 1.38 minus 1.45.
And so this would be your answer for ZL.
So cool. Thank you so much.
And then solving for this one, you have to note that yes, VTH was equal to VX, which you had stated, which was correct.
Awesome.
And then VX minus V over R1 plus VX over ZL.
Equals V. So far, so good. Here comes moment of truth. See if I can do greatest or lowest common denominator.
You want me to do it that way? Okay.
Oh no, you can do it your way because ultimately it'll be the same symbolic. Yeah, Z plus R over RZL. Yeah, let's go. Woo! I can do basic math. Yay. Yeah, so V times Z1 times ZL over R. Yeah. Okay. And then the R1s. Yeah, okay. VZL over. I'm so happy. Okay, sweet. That's amazing. That's amazing.
So from here, you can find like whatever your numbers are, you could then use Wolfram to simplify the ZL over ZL plus R1
Okay.
and get the magnitude of VX.
Oh, VX. Okay.
So to get the magnitude then of this, it will be the magnitude of V, which is V1 in this case. And then the magnitude of ZL over ZL plus R1.
So what does magnitude mean in terms of complex numbers? Do we just ignore the I, or how does that, or no, the I gets factored in, but we take the positive value, or?
So in polar form,
It'll just be the V1.
magnitude of this will be the magnitude of that, which will be V1.
Right.
And in polar form, or I mean in rectangular form, would be the square root of A squared plus BJ.
Oh yeah, that's
Sorry,
right.
ah,
Squared. Right. And what about the Z over ZL plus R1? Because I think ZL had a J, right? Like if we didn't do it symbolically, ZL would have a J.
yeah, so this would be where I would use Wolfram.
Oh, to magnitude that. Okay, cool.
And then find the magnitude and then you just multiply them together.
Together. Great. Thank you.
So that's easier than finding the whole form of it. And then to find the max power is going, sorry, max, I can write max, is going to be 1/8 of the magnitude of VTH over, in this case, you know, the real part of ZL.
Awesome. That's
And that would
awesome.
give you a value of Pmax.
That was huge. If you put that exact circuit on the exam, I would not be sad.
Is it VTH squared?
Yep, thank you. Sorry. Yes, VTH squared.
That's great.
All right, you guys have any other questions? Did this help?
Huge.
Yeah,
This was
that
massive.
helpful. Thank you.
I'm so glad I came to this lecture.
All right. All right. Well, I will post those videos. I still have to re-record them because, as I said, I had some technical difficulties, but now I have this all set up, so I should be able to record them and then I'll post them shortly.
Great.
All right.
Thank you so much. Have a wonderful Thanksgiving,
All right, you guys
everyone.
too.
Yep.
Very,
See ya.
Bye.
very
See
quick
ya.
question with me, but
Oh, sorry. Did you have more questions?
well, yeah, it was just more about like how to understand like the average power complex and their parent, like their application wise of them, or like I can calculate them, but I just don't have a conceptual or like
Okay.
intuition for them.
Sorry, just 1 second. I have somebody trying to get in. Just 1 minute.
Okay.
Sorry, I just had to let a person in. Okay, so you wanted more clarification about like the power terms.
Yeah,
Like you wanted, what exactly do you want to know about them? You feel like you know how to calculate them?
but I
Is that-
just don't have like a understanding of what they really are, what matters with them. Like, I can get them, but yeah.
Okay.
Also, real quick, is this lecture going to be recorded and posted or?
Yep.
Okay.
Yep, I will post this. I realized that I have not been able to post the other one. So I will post them with all the other videos from last week. Okay, let me get to the right.
Awesome. When we look at like a power tool and it says like, or an appliance and it says like 1,200 watts, is that like the real power or the apparent power?
That
Oh,
will
cool.
be the apparent power.
Cool. All right. Well, I'm out. Good luck. Thanks so much.
See you, Ian.
Bye.
Okay, so starting off, you said like average. Do you understand what the average means?
Yeah,
An
I
average,
guess.
just in general, like what an average means.
Yeah, it makes
Okay.
sense.
And then the RMS, you understand that that's like the, because we're now working with sinusoids, the average would be 0. And so we use that as a number to be able to kind of make a definition of an average now for AC signals.
Yeah, that makes
Okay.
sense.
All right.
I guess it's more about like apparent power and like complex power and like reactive and absorption type of deal with them. I'm
Okay.
confused on.
Okay, let me think of how to describe this a little bit better. So complex power is so I think why it gets confusing is because we think of things as like, yeah, they're, they're tangible and real. But the S domain is not a real domain. It is a domain that we use so that we can move things from the time domain into a different domain so that we can do the algebra much easier. Does that make sense?
Yeah,
Okay.
like Laplace.
Yep. So same idea with the complex power is that we are now having AC power. And so to manipulate it, we want to move to the S domain. And in the S domain, we've just defined these terms and they don't necessarily like tangibly mean anything. So what means anything is that PF factor, the power factor. So the power factor gives us a number in the end, like it will be 0.5, 0.8. And what that means is now we can use that to compare to different systems and say it has this power factor. That power factor means something. The more you get closer to 1, that means the more real form it has. And the farther, like the lower the number, the more elements in it that are time dependent. So it has more of a characteristics of having an inductor and a capacitor in it. So those are what kind of mean a tangible thing to us is the PF factor, and then whether, and then we can understand like leading and lagging. So to get the PF factor, we have to use that apparent power number. And then we get the magnitude in the complex domain to be able to get that number. So the apparent power, like it by itself doesn't mean anything. The real portion of it and the average power means something, because in the real domain, we can understand that value. That can be 10 watts, that can be 20 watts. And like, yes, we understand what that means, but reactive power doesn't mean anything. It just means that there is power that's being contributed from time-dependent elements in there. And so does that make more sense?
Yeah.
So the power factor is what we actually use out of that, and that power factor is calculated by that apparent power S. And so again, we just use we use the complex domain to find all these numbers, and then we will interpret them using the power factor basically. So the power factor is what we take away from the complex power, but we kind of want to understand the terms, because when you go take power or even talk about power systems, they will have these terms in there. And the reactive power, again, is just like a value to it, doesn't mean anything per se, but the power factor itself will mean like, is it have more real components and characteristics, or does it act more like a system that has those capacitors and inductors in them? I don't know, did that answer your question fully?
Just to clarify, you're saying the closer it is to 1, it has less components that are capacitors and inductors.
Correct. So if it's
So less
equal to 1,
imaginary.
correct. So less like an imaginary portion to it. And if it is equal to 1, it will be all real elements. So there's no time dependent elements typically in there, or the time dependencies do cancel out, so you don't have any contribution from them.
So they're just all passive.
Yeah, they would just be resistive
Okay.
with a power factor of 1.
Okay then. And in the sense you state that we go into like apparent power or like into the S domain, you couldn't calculate power factor without going into them, right?
Correct.
Or like, because going into the S domain just makes it easier to calculate, but if you weren't going to go the easy way, you couldn't get to power factor because it's just too hard. It's not possible.
Well, again, like it's not the S domain, but the complex domain for this one. So the complex has that J component to it. And so if it only has like real elements and it's just an R value, just lumped up R values, then you're only going to get real value. Like it would only be a value of like 10. And so when you change that into like the complex domain, 0 is with the J portion of it. So it would be 10 plus 0J would be what you would write. And then you could still like calculate out the apparent power, which would just be the magnitude of 10. And then your power factor would be the average of it, average would be 10 over 10, which gives you a power factor of 1.
Okay. And sorry to keep asking.
No, it's okay.
Like literally forgot. What's the power factor is unitless, right? In a sense.
Yeah.
Because it's just a factor of this.
It would be watts. It's watts over watts, or watts over VAR.
So I understand that it's like a percentage, or like closer to 1 is more real elements, but like, is it just like, how would you see that in the real world? Like, would you see like, oh, it has a power factor of like 0.8, and you're like, I don't know what's in it, but it has less inductors or capacitors in it by just looking at that number?
Yeah, so like a power factor of 0.8 would have more resistiveness to it than inductors and capacitors. And then a power factor of 0.2 is going to have a lot of inductance and capacitance that's going. And what you take away from that is that that's going to have a lot more of an effect, like with different loads, and what kind of a load you put on it. And so you just it gives you more knowledge about the system, not necessarily how it reacts or what it responds to, but more of a characteristic itself about with having more resistance or more capacitance inductors in there.
Okay, so power factor is just a characteristic of a circuit that you don't really know much about.
Yeah, 0.8 doesn't mean anything except for it's more of like closer to resistive, and a 0.2 is less close to that resistive. So it's only a comparison of itself. It doesn't really tell you anything real specific, but how far or close are you to a resistive only network or system? Resistive only system.
Well, that makes a lot more sense now. Yeah.
Yeah. Again, there's a lot of different terms for this one, this unit. Gives you more of a description of that purely resistive. You see there's no phase changes between
Mhm.
V and I, and then that's a PF of 1.
And this is I forget where it's like lagging, so I will be lagging V.
Yeah,
It's
so
like
it's a
the
comparison
power.
between I and V.
So with this power factor, we can look at this power factor to determine it's like how much it lags as well
Hmm.
between the currents and voltages there. Just that's the only thing you really know.
Yeah, so when you've put on a source to this system, do the elements in it create a lag between like when I've applied my voltage, there's a lot of lag, you know, there could be a lot of lag or a little lag, and then you finally see like a current, like the current is finally responding to that voltage input. And then if it's the other way and your current leads it, it means that like your current is super quick to respond, and so it's actually giving a response before the voltage changes.
Okay, I guess
I
that
don't know if
makes
that
sense.
helps to like
Just
visualize
to
that a little
ask
bit.
for like applications of like when you want it to be leading or lagging, like or in phase, why would you want those 3 states for it?
So a lot of times you want, I don't have like offhand specific examples, but there are times in certain systems where you're like mostly, well, I won't say mostly. So, well, maybe I can think of one. So like a control system, when you have a control system, sometimes you want there to be a delay. And so you would have, like, you would want it to delay. And then once it sees that delay time, and then it wants to act on that, then you would have it. So that way you could, you know, you can predict exactly how long. Once I've turned on a voltage, I want the system to kind of actually really turn on after everything's been charged after 10 seconds. You know, you could use a circuitry to kind of do that. The current leading is usually a little bit for different applications. And then you're talking about the phase shifting of it. And so with that, you're going to want to do it in applications where you have a phase shift need. I'm trying to think of when. I can't think offhand like what type of an application you would want for that one. See if they give what they give here for those. Okay, that one didn't really describe very well. Like the shifting, it gives you a good example for that, but not of a shifting one. So most of the time, what we use this for and this knowledge for is to be able to create the system to do it specifically. So there's going to always be parasitic effects in a system. So a lot of times you'll look at and measure your parasitics, and then you'll want to create a circuitry that kind of like balances that. So meaning that a parasitic effect of a system is things you don't like. It will be from the wires. It will be from the packaging itself or something else that like you can't change that because that's the way it is. It can have an inductance to it or it could have a capacitance to it. And so most of the time we want to eliminate those effects. And so you may measure, you know, what the full system does, knowing what your circuitry should do. And then you'll like shift the phases due to like adding in an extra capacitor or adding in an inductor to like remove down that effect and try to minimize it. Does that make sense?
Yeah, I guess that makes sense.
Yeah, so you want to kind of get the resultant of the parasitic effect plus what you add into the system to kind of be nulled out. And so that's like the majority of the time what we're doing with these kind of systems is like, let's nullify the effect from a parasitic. And with that, then you're just going to be shifting, like if it does have a factor of, oh, it looks like it's giving you an inductance, then we want to add in a capacitor to kind of offset it.
Oh,
So that
yeah.
your apparent, equivalent is a summation of the two. And you can reduce that effect. So that's the majority of the time are those. There are specific, I just can't think of like an application offhand for the phase shifting for some reason, but control system
That's okay.
is another example of like when you want to usually lag a system.
Mhm.
It's usually for, and it can't just, it can be other things where you just want to, your timing is very critical.
Okay.
All right.
All right. Thank you.
Any other questions? Hopefully that helped to
Yeah.
visualize that a lot better.
Yeah, that really helped. Thank
All
you.
right. Well, have a
All
great day and we'll see you guys next week. Have a great
All right.
Thanksgiving.
All right.
You too.
You too.
Bye.